Hi, my name is Kitty Wong, and I'll be covering my black hole lab. The purpose of this lab is to find the mass of a black hole based on information about a star's motion, and to find the initial velocity of a spaceship to avoid the black hole. At the end of the lab, I could calculate the value of the mass of the black hole and the necessary initial velocity of the spaceship. One principle we use is Newton's second law, which states that the acceleration of an object is dependent on the net force acting upon the object and the mass of the object. Newton's second law also includes the momentum principle, which can be used to derive the velocity and position update formulas. We use Newton's second law here because we need to find the net force acting on an object by summing its forces from interactions with other objects. Another principle we use is the universal gravitational force, which allows us to calculate the force exerted on an object, such as a spaceship, by another object, such as a black hole. One thing to note is that since universal gravitational force is a non-constant force, the average velocity can be approximated to the final velocity when using the position update formula. For part 1 of the lab, my system was a black hole, my surroundings was a star, and my initial conditions are shown here. For the code, I found the initial and final momentum vectors, the star's change in velocity and momentum, Fnet, and its components. This information is used to find the mass of the black hole. When calculating Fnet perpendicular, an important thing to note is that Fnet is equal to the sum of its components, so Fnet perpendicular is equal to the net force minus its parallel component. And I also drew arrows to represent Fnet and its components. These are the results I got for part 1. Something interesting I noticed was that Fnet got larger when the star was closer to the black hole and smaller as the star traveled farther away. This is because the star experienced a greater force of attraction as its distance to the black hole decreased. For part 2 of the lab, my system was the spaceship, my surroundings was the black hole, and the planet, and the only initial condition I changed was the mass of the black hole which I calculated from the previous part. For the code, I found the distance vectors needed for the universal gravitational force formula, and I used the equation of universal gravitational force that doesn't need the r hat vector. That's why the magnitude is raised to the power of 3 and is multiplied by the distance vector. Then I found the net forces and also used the velocity and position update formulas to find the ship's position. These are my results from part 2. I found the initial velocity required for the spaceship to get close to the black hole while avoiding the planet and the black hole. The negative x component means the ship is moving to the left at first, and its positive y component means the ship is moving up. Some possible sources of error could have been running the program for too short of a period of time in part 1, resulting in a less accurate average mass. And in part 2, I used guess and check to find my initial velocity, so it's not the most accurate velocity. For our what does it mean question, we see that the net force is equal to the change in momentum when we calculate the two quantities, but some differences include the direction of Fnet perpendicular and Fnet parallel. They're easy to observe but harder to measure. Also, the rate of change of momentum is easy to observe and measure because we only need an object's mass, velocity, and a time interval to calculate. For our what-if question, my initial velocity needed to have a lower x velocity and a slightly higher y velocity. I knew the x velocity needed to be lower because in my original velocity, the large x component of velocity allowed the spaceship to escape the black hole's gravitational pull. So in conclusion, we calculated the mass of a black hole and found the initial velocity needed for the spaceship to avoid crashing into anything. We used Newton's second law and the universal gravitational force, and we observed similarities and differences between the change in momentum and the net force.